Hey there, class. We're here today. We're going to look at example number 1 from our two-dimensional notes. Now, this is a lawnmower here, and you'll notice this lawnmower is going to move 250 meters. Okay, and while that happens, there is a person pushing with this force right here. So we're going to actually take that force and we'll draw it into a free body diagram here in just a moment. Notice that it is moving at a constant speed. So of course, as always, constant speed means that there is zero acceleration. So let's take a look at a free body diagram. Notice here in my free body diagram, I have my applied force that's on the lawnmower. I'm going to just abbreviate with LM for lawnmower here, and that's by the person. This is a force that's applied at an angle. So right away when I see angles, I'm thinking I need to do something with force components. I have the gravity pulling it down, and I have the normal force that's pushing up. Now you'll notice that this normal force is larger than the force of gravity. And that's because not only does the normal force have to support the force of gravity, but it also has to support the y component of the applied force as well. We then have the force of friction that's going to oppose the applied force. So let's come up with a strategy to find the amount of work that's done by the person. So basically, my strategy, because we know that work is going to be force times displacement, is that we want to find the component of the force that's applied along the x-axis, because it's moving along the x-axis, so we need that component. Keep in mind, the way I solve these is I like to look at displacement and force as being vectors, and they must be parallel to one another. So the force that we substitute into here has to be parallel to the displacement. And again, in our if we go back to our picture, you'll notice the displacement's along the x-axis, so we're going to need the x component of this applied force. So what I've done over here is I have drawn the applied force and then its x component. To find the x components, this is the adjacent side of our triangle, and therefore we're going to use the cosine function. When I solve it for the applied force in the x direction, it's going to be the applied force times cosine theta, which of course in our case is 45 newtons and 60 degrees here. Now the second part was to then apply my work equation. So the work is done by the applied force in the x direction times the displacement. Both of these were positive values, so therefore we're expecting a positive value, not positive in the sense of a direction, but positive in simply the sense that it's not negative. So we substitute those in, and we end up with 5,625 joules worth of work. Now the next part B, asks us to find the actual force of friction. One way to do that would be to know the coefficient of friction, but we don't actually have that. What we do have, though, is we do know the applied force. Let me go back to my free body diagram. We do know this applied force that's here, and we know that the force of friction is back this way. The fact that there's zero acceleration tells me that this force here and the force that goes along the x-axis must be balanced. They must total out to be zero. So basically, I'm going to use a net force equation in the x direction and solve it for the force of friction. So net force equations always start with Newton's second law. I substitute in the forces that are along the axis. In this case, there's only two: the applied force in the x direction and the force of friction. These are vectors, so we're adding them together as our equation tells us. The acceleration is zero because it's moving at a constant speed. Solving this for the force of friction, I'm going to have to subtract the applied force in the x direction over to the other side. So that's where I get the negative from. And then I substitute this in. This actually came from up here at the beginning when I found the force applied in the x direction. And I get a, looks like a negative 22.5 newtons for the force of friction. Now the question specifically asks here, how much, which doesn't really ask about the direction at all. It's just really more of a magnitude question. So I find I'll just ignore the direction part when I respond and get 22.5 newtons. Now, one other note that I wanted to make a mention of is that, again, the equation I typically use is, for work that is a force times a displacement. Both of these are being vectors. Another way to look at this, an alternate way that I've seen before, is simply just force times distance times the cosine of the angle between these two things. And if you noticed, this is actually exactly what we get right here. Again, here's the force, there's our displacement or our distance, and then there's the cosine of the angle. So this is just in a different kind of order, but again, order doesn't matter with multiplication. So this actually turns out to be the exact same thing we did as well. So either way would suffice here, but in the end, it's all going to work out, and these are what we should get for our responses.